Hello, this is William,
Jay.
and this is our presentation regarding model simulation and analysis of the 6U3 building. So the presentation is going to be consisted of seven regions. The firstly, introduction, second, objective motivation, thirdly, methodology, fourth, preliminary studies, fifth, 6U3 building model, sixth, model analysis, and seven, discussions.
To begin with, the 63 Square is located in Yeouido on an island that is on Han River in Seoul. The construction happened between 1980 to 1985, and the total height is 249 meters. And there is 60 floors above the ground and an additional 3 basement level. This was designed by Shinmyung Park, and the golden reflective glass represents the rising sun over the Han River. It was the tallest building in Seoul when it was first built, and it was built as a Seoul's landmark for the 1988 Seoul Olympics. It's known for its 63 art and 63 aquarium, 63 sky deck, which is known for its arts. The main objective was to analyze the 63 Square model, and the motivation was it is a building that represents Seoul, and Yeouido is known for having extreme wind. We thought we had to understand the dynamic response, and we noticed that the model analysis was the fundamental of this dynamic response.
To analyze a 63 building, we use the finite elements method, which is used to analyze the fittedness of a structure by analyzing and merging small divided meshes separately. First, as with the utilization of equilibrium, we calculate and predict the amount of force acted on each mesh. Then, using constitutive equations, we calculate and predict the movement of each mesh according to the material. For instance, Hooke's law, F equals Kx, is a specific constitutive equation for elastic materials. And lastly, using computable equations, we alter and match the result of each mesh to neighboring meshes, which produces a physically reasonable result. Also, we have utilized structural dynamics, which analyzes the behavior of structural subjectives to dynamic loadings. Dynamic loadings include people, wind, wave, traffic, and earthquake. This can be used to find time history, which includes displacement, velocity, and acceleration, and more significantly, can be used to find model analysis. This is significant as it analyzes the inherent dynamic property of the structure, and also due to the hazard of resonance of the structure and natural stimulus.
Now moving on to the preliminary studies, which is understanding the model analysis with the usage of casework. The first case is regarding the New York City Pencil Tower. And for the methodology we used, we have identified the length, width, height of the actual model, and we scaled it to 1 to 2 to 20, 1 to 1 to 20. And the material we used was construction steel, as it was the major material used to craft the building. And this is the information regarding the building, which includes the details. And moving on, what is mesh element method? So a mesh is a discrete representation of continuous geometric domain, which uses in numerical simulation. And we have used finite element method. And the mesh divides into the domain into triangles or quadrilaterals, as well as tetrahedra and hexahedra. And they tell us like the approximate physical behavior of what the object looks. And for the first model, we use 3 mesh elements, and
we also observed each natural frequency for 10 different modes. And then we looked into 5 different mesh elements and observed the natural frequency for 10 different modes. And last looked into 10 mesh elements and looked into 10 different modes for natural frequency. As we can see, the visual observation was difficult to see any significant changes between different mesh elements numbers. However, as highlighted, we can see a difference in the natural frequency value for mode 5 and 10, which varies from 39, 38, and 35 hertz for mode 5, and 106, 79, 68 hertz for mode 10. And these are the recorded videos for the 10 different modes of each mesh element's numbers. So as you can see, each modes represents a different direction and force affected to the tensile tower models.
Now moving on to the Petrona building. This was the structural system of the Petrona Tower. It was primarily built by concrete, and the concrete was used as the central core. So in this case, we also utilize the concrete elements as a material for our ANSYS. And these are some information regarding the Petrona Tower, which the two towers are connected through the sky bridge. And as well as the structural system of the tower is compromised of 25 meters to 25 meters. And there are 16 cylindrical columns, which are constructed using high-strength reinforced concrete. So the significance of the model analysis. So the ratios were used identically to imitate the building, although it's not the same building. It's an H-shaped model that shows the total deformation regarding the usage of ANSYS. So this is how the H model reacts to each different deformation. The first deformation was when the mode was set to 1, and you could see a front to back movement. Now this was when the mode was set to 2, which is total deformation is 2. It had a left to right side sway. For number 3, there was more of a twisting dynamic of the model. Now for number 4, you can see how the model diverges into two opposite directions. And for number 5, you can see it diverging while twisting. So this was the conclusion we got for the results using ANSYS. So when the mode increased, the frequency level of hertz also increased, and we could see a significant increase in the frequency level from 3 to 4, and this was because the bridge in between the structure fluctuated a lot as the mode increased.
Next is a stable structure. I did this investigation to investigate how the different model respond to sensitivity. So I made 5 models. First one was the 2D model, and the second was the 3D Bayesian model, which was constructed with the structural steel. To make the model asymmetric, I only changed one of the legs to other materials. The first one was the silicon, and the next one is wood, and the last one was stainless steel. So this is the video of the 2D model. It fluctuates back and forth.
And this is the movement of the 3D model when the mode is equal to 1. It moves backward and forward. And this is mode 2. It moves sideward. And this is mode 3. And this one is mode 3. Mode 4 is kind of twist. And lastly, this is mode 5. So this is the result of the frequency of the basic model with the dynamic analysis. And this is the 3D model with different materials. As you can see here, like the models of basic, the structural steel and silicon and stainless steel is similar. But when you see the wood model, you can see the red region is much more bigger than others. And in here, the different materials are the place where the minimum force is asserted to. You can see that the others are kind of similar.
As the red model is the most prominent for the wood, this shows how the tension level with one leg consisted of wood is the most fragile among the ones.
So there were some considerations that we decided to make during creating the model. The first was to consider the actual dimensions. Secondly, you decided to customize it to look as similar as possible. And lastly, we decided in order to make the dynamic property similar to the actual structure, we investigated the structural dynamics. We made a model that resembles the building first. And in the first trial, we only had copied the outer looks, which wasn't valid because it was colliding into each other. So we decided to consider the inner shape. Consider the inner shape, which showed the results that satisfied our expectations.
Next, to make the model similar to the real building, we tried to match the natural frequency of the model and the real building. So I tried to find the natural frequency of the 63 square. However, there wasn't a real research about this particular building. So instead of the 63 building, I found the research about the Taipei 101. It says that the natural frequency of this building is 0.15. Based on the other research, which is about the fundamental natural frequencies of building research, I found this formula to kind of predict of the natural frequency of a building based on its height. So in this formula, F equals 46 above H. F is frequency and H is the height of the building. So when I substitute the formula, substitute the height of the building, 250, to the formula, I got that the natural frequency of the 63 square is equal to 0.2. So our goal was to make the frequency of the model equal to 0.2 to 0.4. So I kind of like make a hole in the building. I make it empty in the bottom and fill it up the upper part. So I got the frequency of points, as you can see here, 0.3666. So after this, we're going to investigate how this model, which has the same natural frequency with the real building, reacts to the laws like wind and earthquake or things. So Thank you. This was our presentation about the 63 square and its analysis.